We're going to look at some things about how fluids flow, like when they're moving through pipes and stuff like that. And an assumption we're going to make is that this fluid is incompressible, which means that it cannot be compressed. So if you apply pressure to it, the volume doesn't change. In general, when we talk about fluids, fluid could be either a gas or a liquid. But if we're talking about an incompressible fluid, that is really not a good approximation for a gas. You know that gases change volume with pressure, PV equals nRT, and so that doesn't really work. But for a liquid, assuming that our fluid is incompressible is a pretty good assumption. If you apply a lot of pressure, a liquid will compress a little bit, but the amount that it does compress under normal circumstances is negligible, and so this assumption is safe. Some of the principles that we'll talk about also apply to gases, but the equations we'll derive only apply to incompressible fluids, and therefore to most liquids are a pretty good approximation of an incompressible fluid. So if we consider this pipe, and I've made this pipe sort of goofy. This part's kind of normal, but then it, flows around in weird shapes. If we consider the fluid flowing past this given point right here versus the fluid going past this point, it makes sense that the amount of fluid flowing past here should be the same. This fluid can't stack up here in this area, so anything that comes in here, that pushes out fluid at the other end. Likewise, if fluid goes past here, then that same amount of fluid will have to go past this point because there's just no other place for it to go. And the same thing here, same amount of fluid will go past this point over here. So that's regardless of how wide the pipe is or how much it curls around or anything like that. So from that, we can say that, and that's a volume. The volume of fluid that flows past has to be the same. So the volume flow past this point, this first point, must be equal to the volume flow past the second point. Now the volume going past a given point is equal to the cross-sectional area times the velocity of the fluid times time. Right? Velocity is meters per second, meters squared, seconds. You can see the dimensions work out. And therefore the mass flowing by this first point, and also the mass flowing by this point is equal to the rho times the volume flowing past, which is equal to rho times area times velocity times time. I know this is confusing because we have volume and velocity in the same equation, but bear with me. And similarly, we can say that the mass flowing by part 2 is equal to rho 2 A2 B2 D. Right? And equating these, because the amount of fluid flowing past these points has to be the same, we can set these two equal to each other and say that rho 1 A1 B1 equals rho 2 A2 B2. And if we're just talking about a single fluid, then these are the same rho, and the time is of course the same. So we can say the area, cross-sectional area of this first part times the velocity here must be equal to area at the second part times the velocity at the second part. And this is true. This is called the continuity equation. And this is true for any kind of pipe, whatnot. This is why if you have an attachment on a hose and you want to spray something further, it comes to a narrower point. That is a smaller cross-sectional area, and therefore the velocity of the water going through that increases to keep the same amount of water flowing out at a given time. That's also why there are, you have different kind of spray things on sinks a lot of times. One is just kind of solid is pouring out. Then usually you can turn the little knob and then it shoots out a bunch of little holes, and that's decreasing the area that it's traveling through and therefore giving you a greater velocity of the water, which can be useful for cleaning things because you get more pressure to knock off gunk off your dishes. An example of applying the continuity equation The water is flowing out of a hose with circular cross-section of diameter 2.6 centimeters at a speed of 2.1 meters per second. An attachment is placed on the end of a hose. The water flows out of a circular opening with radius 0.4 centimeters. What speed does the water flow out of the nozzle? This is just applying the continuity equation. It's a circle. Cross-section is a circle, so this area becomes a pi r squared. So we can say pi r1 squared times v1 equals pi r2 squared times v2. Pi's cancel out, of course. The diameter is 2.6 centimeters, which means the radius is 1.3 centimeters. I can see that we're going to divide out the radii, so it doesn't matter what units we use. So 1.3 squared times 2.1 equals 0.4 squared times v2. Oops, I should have written v2 right there. And so the velocity when it flows out of the nozzle then is, we can just calculate by multiplying these together, dividing by 0.4 squared, which comes out to 22.18 meters per second. So just by making this nozzle small, we get a pretty large velocity of water coming out of the hose. Now many equations, many of our problems will apply both the continuity equation and what's called the Bernoulli equation, named after a guy named Bernoulli, as you might guess. And the Bernoulli equation comes from a couple of different sources. Mostly it comes from an analysis of the energy of a fluid as it flows through a pipe or any other sort of container. The equation, as I said, comes from applying conservation of energy. You don't need to know the derivation, but as always, I want to show you where this stuff comes from. If you recall, work was equal to force times distance. We'll assume this force is perpendicular, so we don't have to throw in the cosine theta. And so the work done on a fluid is a force times a distance, and force is pressure times area times distance. And an area times a distance, that's just the volume of water that's gone through. So that's pressure times volume. I'll call this delta volume. It's the amount of volume that's flowed past. So this is, if we consider a pipe, we consider a section of fluid, this would be pressure on this side. Over here, we consider there is another force on this side. So the net force is P1 delta V1 minus P2 delta V2. So there's a force to the right from here and a force to the left from there. Okay. Now, this would be a sort of a pushing force. That's non-conservative. We know non-conservative work is equal to delta KE plus delta PE. So we can say P1 delta V1 minus P2 delta V2 equals 1/2 M, and we call this delta M because it's the amount of fluid flowing past, V2 squared minus V1 squared plus mg delta y. Okay, and we're going to split this up, so I'm going to write this as y2 minus y1. Alright, now we know mass, the amount of mass flowing by is just rho times the delta V. So this, so making that substitution, we can say P1 delta V minus P2 delta V, and delta V1, delta V2 are going to be the same thing because the same volume flows past both places according to the continuity equation, is equal to 1/2 rho delta V V2 squared minus V1 squared plus rho delta V G Y2 minus Y1. Okay. And then if we just do a little bit of rearranging here, well, first off, we can see there's a delta V in every term, so those go away. And if we collect all of our ones on one side, we get pressure 1 plus 1/2 rho v1 squared plus rho g y1 equals pressure 2 plus 1/2 rho v2 squared plus, oops, not p, rho g y2. And so at any 2 points in the fluid, this quantity of pressure plus half times rho times v1 squared plus rho times g times y is going to be equal. This is the Bernoulli equation. And we can see a couple things.
I finished it.
There are a couple of relationships we can see in the Bernoulli equation. If we ignore the height for a second, we can see that for if you're at the same height, if we increase the pressure, then we have to decrease the velocity to compensate. Likewise, if we increase the velocity, we have to decrease the pressure to compensate. If we want to keep the velocity the same, which may be important in fluid flowing through pipes in like a city sewer system and stuff like that, then we have, if we go up to a higher height, then we need to decrease the pressure to compensate, and so forth. And as I said, a lot of times we will, to solve problems, we will apply both the Bernoulli equation and the continuity equation together. Most often you'll use the continuity equation to calculate a velocity, and then you'll plug it in to the Bernoulli equation to find something else. We'll also be applying the Bernoulli equation to the lab we're going to do. Basically, we're going to have a container that's full of water, and then we're going to cut a hole down here, and we're going to let the water flow out, and it'll go down and into our parabolic path. Once the water leaves this bucket, it's following our normal kinematic equations. Since there is no initial vertical velocity, we can say our y final, which is 0, is equal to y naught minus 4.9 t squared, and our x is just equal to velocity times time. So we're going to use this to figure out what the velocity is of the water coming out of there. The pressure at both places is basically atmospheric pressure, so the pressure in this equation goes away. And we're also going to say that the water level up here, while it is changing as water flows out, it's not changing very quickly, so we're going to neglect this term. So basically that reduces our Bernoulli equation to rho g y1 equals 1/2 rho v2 squared plus rho g y2. So we can cancel out rows, move this over here, multiply by 2 and take a square root, and figure out that this velocity is equal to the square root of 2g delta y. And that's the equation we're going to use for our lab. So we're going to calculate this velocity, figure out where the water lands and calculate the velocities in kinematics and compare it to this value that we should get. This is called Torricelli's law. Not that you really need to know that, but some guy named Torricelli reduced the Bernoulli equation to that.